3, 2, 1, let's go. Here we are, 7.5, finishing up our wonderful journey into the world of Laplace transforms with a peculiar function. All right, so let's motivate what the Dirac, which is the pronunciation of that word, delta function is. Okay, so something we know is that the Laplace transform of the constant function 1 is 1 over s. Right, that's hopefully burned somewhere into our brains right now. And thus, with this knowledge, I can tell you the inverse Laplace of 1 over s is equal to 1. Alright, so what's my question going to be? Well, my question is going to be the following. Can I find something whose inverse Laplace is 1? Right? What does it equal? Well, does it equal anything, right? You always want to answer that question first before you go hunting a dragon and make sure dragons exist. Alright, so to make this a little bit more precise, what we're really looking for is a function delta t, hey, Dirac delta, with the property that when I look at the integral from 0 to infinity of e to the negative st, delta t dt, I get 1. Okay, right, that would mean the Laplace transform of the Dirac delta is 1, meaning the inverse Laplace of 1 is the Dirac delta. Okay, so that's the goal for today. Find a thing that does this. Now, before we start setting up how we're going to create such a thing, let's think about what it's going to have to do. Right, so when we do the Laplace transform, we do this integration, it eliminates the variable t, and thus we get something that depends only on the variable s. Now, on the right-hand side here, I have the constant function 1, meaning that this integration, not only must it eliminate the variable t, it's going to have to also eliminate the variable s for me. Okay. Now, if I think about how would I get rid of a dependence on s here, well, this function is basically going to have to, annihilate most of e to the negative st. Right, because if it doesn't, if there's some parts of this function left over, well, then there's some dependence on s, and the integration will get rid of the t variable, but leave me the s's. Right, note that e to the 0 is 1. Okay, so if I basically ensure that this function gets obliterated other than what's happening nearby at 0, then e to the negative s0 is just 1, and thus there's no s dependence. That's the idea. Right? We need a function that's basically going to completely and utterly overpower this e to the negative st, except nearby 0, where basically the s will get crushed because t of 0 will delete it up in the top. Alright, so that's the idea. So how are we going to do it? Well, we're going to set up these functions first. So for each positive integer n, define delta sub n of t to be the following function. Right, so this is a difference of two Heaviside functions, 2 unit step functions, and I've scaled it by n. So specifically, I just needed to create the function that is 0 for a majority of its inputs, but nearby t is not 0. Right, so nearby 0 is non-zero. Right, so as n gets really big, this function is basically 0 everywhere, except for in a small little window where it actually has some values. So specifically, there's a little window by 0 so that it actually spits something out. And I'm picking n for reasons that will become apparent as we go forward. If we just had this be 1, it turns out what we're about to do is not going to work. So the multiply by n here is going to be clear once we get there. Right, but as I was describing that before, the function we're going to want is going to basically just completely decimate the e to the negative st, except for t values close to 0, right? And this works out, right? Just imagine what this looks like for n equals 100 even, right? In the window 0 to 1 over 100, it takes the value 100, it's the constant function 100, but literally everywhere else it's identically 0. So there's a small little window where it takes a pretty big value, but outside of it, it's totally 0. Now, when I go ahead and take the Laplace transform of this, so like I was saying, right, the majority of the e to the negative st gets deleted, except on the window 0 to 1 over n, right? And we want this really small window close to 0 because e to the 0 is 1, right? And that will remove the s dependence, right? Because you want this Laplace transform to have no dependence on the variable s, so we got to get rid of it somehow. All right, well, let me do this integral. So work out the details. It's that the n goes along for the ride, e to the negative st all over s, negative of that. We've seen that multiple times now. Plug in the bounds, t is 0, and t is equal to 1 over n. And there we go. So we plugged in the 0, so hey, got rid of the s over there. Now there's still an s up here, and s is down here, and we'll deal with them shortly. All right, now I'm going to clean this up in a very specific way. I have an n and an n right there, so I'm going to factor that all out and clean it up a little bit, and now it looks like this. Okay. So, what am I going to do? All right. Well, so for each n, I created this thing, and note, as n gets bigger and bigger and bigger, the window here gets smaller and smaller and smaller and smaller. So I want to take a limit, right? Anytime we do something like that, the goal is take a limit. All right. Now, before we even do the limit, if you look at this, you'll see that term right here on the left is going to go to infinity. E to the negative s over n, I don't care what s is, n gets big enough to delete it, and we get e to the 0, but then we've got 1 minus 1, so we have an infinity times 0 limit here, so we got to go to the hospital. All right, so let's take the limit, and like I said, we're going to want to hospitalize this one, so I'm going to sneak my n down into the denominator by putting its reciprocal down there. Ask my good friend L'Hopital to help me with the limit. We take the derivative of the top, derivative of the bottom, and conveniently, a bunch of magic happens now, right? The derivatives introduce this term in the top and this term in the bottom, and they knock each other out. And then now I take this limit, which we already know what that's going to do. Hey, there's that e to the 0 I was talking about. Look, the s dependence has now been completely removed. Exactly what we wanted it to do. So now we've got 1. Excellent. So let's group this all together now. Let's define the Dirac delta to be the limit of those delta sub n's. So note here, we're creating a function by taking a limit of functions. If I look at the Laplace transform of the Dirac delta, this thing in here is the limit of these sort of like step Dirac deltas. They're not the Dirac delta, they're the ingredients to make it using a limit. As we've discussed, we can pull limits out of integrals. It's totally fine. Can't stop me. As we just noted, this improper integral in here turns into that term right there, and as we just demonstrated, that limit is indeed equal to 1, and bam, boom, totally done, we've got it. The Dirac delta is the function whose Laplace transform is the constant function 1. Nice. So, like I said, this construction, making these delta sub n's, right, that whole little window of, right, it's basically 0 everywhere except on a nice little small window near 0, so we want to grab that e to the 0 term, right, at 0, e to the 0 would be 1, right, and we want to make that little window as small as possible to eliminate all possible s dependency. And we pulled it off, and then that multiply by n was needed here, because without that there, then this limit would have actually been 0, and we don't want that. We want the Laplace transform to be 1. Okay. So if we didn't do that, let me jump back there. This whole multiply by n thing right here, we wouldn't have this n right there, and that wouldn't give us the limit we wanted. So we just snuck it in, and it gave us what I wanted. Beautiful. All right. Well, you should be highly suspicious of every single thing I just did. Okay, right? Why should you be highly suspicious? Well, the Dirac delta is not a function. right? Let's think about what its values would be. So those step Dirac deltas that we made, those functions that on a nice little window, on a small little domain, by 0 is non-zero, but everywhere else is 0. If I were to actually take the limit, what do I have? Well, you'd get this. Right, for every t-value that's not 0, eventually this window will get smaller than it, and the delta spin will kill it. It'll just spit out 0. However, at 0, it's constantly having a value, but it's constantly spitting out a bigger and bigger and bigger and bigger and larger and larger and larger value. So, yeah, at 0, it's technically infinity, I guess. I mean, infinity's not a number, so it's not really right, but this is how it's written, right? It turns out that the Dirac delta is not a real function, but rather it's something that's known as a distribution, which is also called a generalized function. And these are essentially things that can be represented as limits of appropriate functions. There's a highly technical definition of what a distribution is supposed to be, but the basic gist of it is that it is something that you can reasonably approximate using a limit. Right? Even if in the limit the actual thing doesn't make any damn sense, it's still fine, and it turns out everything works out. So Dirac was the first one to use this idea of a distribution or a generalized function. The classic physics principle of I'd rather be right than rigorous. Paul Dirac, who Dirac delta is named after, was using these to solve differential equations. He was getting correct answers, and basically mathematicians had to come in and figure out why the hell all of this garbage he was doing was actually working. Specifically, a mathematician named Laurent Schwartz came in and cleaned it all up. And actually, this is pretty recent. This was 1945 when all of this stuff got cleaned up. So this is not even 100-year-old mathematics, which is nice, considering math's been around since the dawn of time. Okay, so if you're interested in learning more about these things, check them out. They're called distributions. There's a lot of build up to them. You need a lot of tools to make all of what I just did, mathematically super formal and rigorous. But for the most part, it's going to work. Just treating the Dirac delta as a limit of things. It's fine. All right. So let's actually use this now in a differential equation. Right. Because it turns out, like I said, Dirac delta was, Dirac delta, that's his name, Dirac delta, delta Dirac. Paul Dirac was using these things for differential equations because they show up in modeling of differential equations. Specifically, consider the following physical situation. Let's say we got a mass spring, no dampening. Mass is 1, spring constant is 1, make our life as easy as possible. It's at rest in the equilibrium position. So y of 0 is 0, y prime of 0 is 0. All right. Literally, nothing is happening. Okay. So something needs to happen. Okay. So let's say Einstein is trying to get work done, but that pesky von Neumann is blasting music again. Speaking of 1945, this was literally a problem on the campus of Princeton University. Frustrated Einstein takes out a hammer and hits the mass spring system. So now note, a hit like that is instantaneous. It's an impulse, right? There isn't a constant pressure. He doesn't hit it and hold it down. He strikes it with great force. So that's how the Dirac delta comes into play. Because as a differential equation now, this can be modeled as follows. So the mass is mass 1, there's no dampening, so there's no y prime term. The spring constant's 1, making life easy for us. Right, at rest, so no velocity is given to it, and it is at equilibrium, so y of 0 is 0. Right, now if there's no external forces, this mass spring system is never going to do anything. Right, but this is an instantaneous external force, and that's how the Dirac delta comes in. Right, and you can imagine that the way the function is set up is like, at t equals 0, it spikes super high, Right, it blows off to infinity, really big. Right, 2 times infinity is totally a thing. So, right, rather than, a constant amount of pressure held on it for a given amount of time, there's an instantaneous external force that hits it. Right. So, as you can imagine, you can have all sorts of systems like this. Like, imagine, a bridge just sitting there, nothing happening, and then, gets hit out of nowhere by a strong wind. Right, or, I don't want to say anything bad, like a plane crashes into it or something, but, yeah, that works, I guess. Anyway, so in terms of physical modeling, you can use the Dirac delta to model these sort of instantaneous external forces happening. Really nice. Now, as a differential equation, of course, we have to keep in mind that this is not really functions anymore, but rather generalized functions and distributions. But as it turns out, like a lot of things in mathematics, we can actually still get solid answers here by taking Laplace transforms. So let's hit this thing with a Laplace transform and solve for y. Okay. So, take the Laplace transform on both sides. So on the right, we can take the 2 out, because we know the Laplace transform is linear. On the left, we're not going to get anything too exciting, because y of 0 is 0, y prime of 0 is 0. So the left-hand side is going to clean up just super nicely. Now remember, the Laplace transform of the Dirac delta is 1, so we get 2. Alright, keep going, keep cleaning it up. I get s squared plus 1, which lines up with the auxiliary equation of y double prime plus y, so we know I didn't do anything wrong. Now, I have Laplace transform y is 2 over s squared plus 1, and thus I can solve for y. The inverse Laplace of 2 over s squared plus 1 is just 2 sine of t. And there we go. Nice and easy. Well, that's too boring, so let's spice it up. So, let's say Einstein kept this cool for a little bit before he finally lost it. That means the model would look like this. Right, so the Dirac delta there doesn't activate until t equals 1, and at 1 there's this instantaneous external force hitting the mass spring. Alright, so in general we're going to want to know what the Laplace transform of the Dirac delta of t minus a is for any real number a, right? Obviously 1 for our particular example here, but in general it'd be good to know what that Laplace is too. Okay, so recall that shifting the t-axis, a translation in the t-axis, Laplace transforms interact with that quite well once you multiply by a unit step function. And specifically, you get that beautiful formula right there. Alright, now, multiplying the Dirac delta by the unit step function is not going to do anything, because the Dirac delta is 0 everywhere except at t equals a, where it's positive infinity. So multiplying that by 1 will keep us a nice positive infinity. So that holds. So by appealing to this formula up here, we then get the Laplace transform of the Dirac delta. T minus a is actually e to the negative as. So that's interesting. So that tells us that the Dirac delta, once you translate it, once you move the spike away from 0, you actually get s dependency, right? So now you're actually getting a function that depends on s. So interesting. Alright, so let's now use this to solve the differential equation. Now we're going to see it's going to get a little bit more interesting, and that's going to be how we're going to wrap it up for today. Okay, so specifically, if we were to solve this differential equation, then Laplace both sides. Now we know what the left-hand side is going to turn into. And we now know what the right-hand side is going to turn into. 2 is going to go on for the right, and this will be e to the negative as. A in this case is 1, so it's e to the negative s. So I need to find the Laplace transform of y, so that I get 2 e to the negative s, 1 over s squared plus 1. So that means y is the inverse Laplace of that, and now here is the interesting and the more exciting part of it. So remember, we learned how to do inverse Laplaces like this. We didn't say when we were going to see them, but we said that we were going to see them. And now here they are. So now note the 2 is going to go on for the ride. The inverse Laplace of 1 over s squared plus 1 is sine of t. But the e to the negative s is going to cause a shift in the t-axis. Specifically, we get this. Right. So we'll have 2 sine of t minus 1 times the unit step function of t minus 1. Now the solution that I have here, if you think about what this thing is doing, when t is less than 1, the unit step function there is 0. So there is no activity. Right, and by the physical model, we know that Einstein does not hit the mass with a hammer until t equals 1. So this function doesn't activate until t equals 1, and then when it does, it turns on, and then now it acts like a dampened, no damping mass spring system, right? Specifically, it'll just be twice the sine, right? And the 2 there coming from the amount of Newton seconds Einstein imparts onto the mass spring. And there we go. We've done it. Nice. All right, so now we've basically hit all we're going to hit for the Laplace transform. So now we know how to handle quite a bit of second-order linear differential equations. Right, the Laplace transform can handle all the other ones we've talked about, and now it can handle some other interesting ones where the modeling is going to allow for external forces, and not only external forces, but external forces that don't necessarily activate right away, or only have a window, or only allow for, as we saw with the Dirac delta, an instantaneous amount. Okay. That's our story for the Laplace transform. Of course, that's not the full story. There's a lot more that you could do with the Laplace transform, and in fact, there's other transforms out there. The Laplace is not the only one. Maybe somebody named Fourier has an opinion on that one. But, alright, that's it, and we'll say goodbye to Chapter 7.